So it says, well, three things. For one is that, okay, well, I guess let's have it set up first. So you have some sort of population with whatever distribution it has. So you've got some sort of random variable x, whatever it is. Well, if I look at x itself, I really don't know anything. I mean, it could be anything in the world. But instead of looking at x, if I look at, take samples and take the average. So take a particular sample size n. And consider the new random variable x bar. So the central limit theorem says four things. First of all, if I take the mean of these averages, it's the same thing as the mean of the original guy. So that's nice. If I take the standard deviation of the averages, I get the standard deviation of the original guy divided by square root of n. If x happened to be normally distributed, then so is the averages. And the one that's surprising is even if x is not normal distributed, then if the sample size, if n is at least 30, then x bar is basically normal distributed. I mean, it's not quite perfect, but you will never notice the difference. So, I mean, these last two are really important for theory stuff, but honestly, in this class, you can probably not really think about them and get along okay. The main thing, if I'm going to tell you something to remember, is remember this second one. So if you're, like when you're doing this normal distribution stuff, if you're doing like a single result, use the standard deviation they give you. But if they ask you for some result about an average, then you have to divide the standard deviation by square root of n. Is really what it comes down to, as far as like practically getting through problems and stuff. So it says, okay, you've got that correct answer. Because n is at least 30, the sampling distribution of the mean ages is precisely, well, precisely is bad, but okay, because n is at least 30, the sampling can be very, very, very well approximated by a normal distribution with mean of mu and standard deviation sigma over that. Yep, so that's fine. Okay, so women's heights are normally distributed with the mean given by that and standard deviation of that. So if you're doing one woman, you're going to do exactly what we were doing a second ago. You're going to say, okay, we'll do norm dist 65, the mean is 64.4, the standard deviation is that. So part A is exactly what we've been doing. So just go norm, dist. We care about, you can't see it, 65. The mean is 64.4. Standard deviation is 2.8. Oh, and we need a 1. So if we're looking at one woman, there's a 58% chance that she has a height less than 65. So 5848. Okay, but then the point as far as the central limit theorem thing, instead of looking one woman at a time, if we look at a group of women, so 48 of them, you're going to do the same thing, but you've got to divide that standard deviation by square root of 48. So we're still going to do norm dist. The number we care about is 65. The first part of the central limit theorem, the mean of the averages is the same as the mean you started with. So the mean is still 64.4. Same as it was for just a single woman. But when you do standard deviation, you go, well, whatever the standard deviation for a single one was divided by the square root of your sample size. So square root of 48. Wider so it doesn't work right. Whoa, that looks really funny, doesn't it? So norm dist, we still care about 65, the mean still 64.4. 2.8 divided by the square root of the sample size and 1. So if we looked at one woman, the probability of her height being less than 65 inches was 58%. If we look at a group of 48 women on average, there's a really good chance that they're less than 65. So 0.9312. Now let's do one more like that. So the overhead reach distances for adult females are distributed with the mean of 200, standard deviation of 7.8. So first part, we're looking at one woman, and we care about 210 centimeters. So for one woman, it's hard to type one-handed. I should really quit holding the tablet with the other hand. Okay, so we care about 210. The mean is, I'm going to have you all read it. What's 200? What's standard deviation? 7.8. What do I type in last? 1. All right. 90%. Is that what I'm looking for? What's the question actually asked me to find? Probability that greater than 210. Is that what I got? Yeah, this always gives me less than probability. This is a probability it's less than 210. So I'm going to go 1 minus. That's the probability it's greater than 10. All right. Okay, now if I look at a group of 15 women, you might say 15, well, let's not worry about that. So the only thing that really changes I'm going to cheat and copy. Control C. So the number we care about is still 210. The mean is still 200. We still care about 1 for the cumulative. The only thing that changes, if we're looking 15 women at a time, we got to put divided by square root of 15. Okay. And again, we care about 1 minus that. Oh, actually, I take that back. They changed the number on me, didn't they? We don't want 210 anymore. What do we want? 198.7. Okay. So 74.07. Okay, and now here's the question that I guess they do want you to actually understand the theory part. So we can always use the normal distribution if the size is at least 30. Here we don't have 30. But the other thing we can, if the original distribution was normal, then we can also always use the normal distribution, right? And it told us that the original distribution was normal. So that means we can. So let's go to about 33. Engineer, seat was designed for pilots between that and that. The new population of pilots is normally distributed with the mean of that, standard deviation of that. If a pilot is randomly selected, what's the probability his weight is between 120 and 171? So we've done that. We did that last time. How do we do that? We're not looking for greater than, we're not looking for less than, we're looking for between. How do we do that? Okay, it's 125, 27. So if I draw my curve or whatever, here's 125. I care about, I don't remember what the numbers were. It was like 120 to 171 or something. Yeah, 120 to 171. We're looking for the area in between those. So we're looking for that right there. Okay. Which we know if we use the norm dist or whatever, if I put it in 120, it'll give me the area over here. If I put it in 171, it'll give me the area starting all the way back at the beginning. So if I want the area just between them, well, I can take the 171 guy and then subtract off the 120 guy. That'll give me the whole area, then minus this little tail. It'll just give me the area in the middle that I want. So that's what I'm going to do. I'm going to go in here. Pull up the problem again. So the big area is norm dist 171, 125, 27.9, and 1. So that's everybody less than 171 pounds. If I do that again, so norm dist 120, 125, 27.9, and 1. So 95% of people are less than 171, 43% are less than 120. So if I subtract that, I get the number of people between the two of them. So the 95 guy minus the 43 guy. So there's 52 people, 52% of people that are in between. All right. So that's if I look at individual pilots. If I don't care about individual pilots, but I care more about groups of pilots, I'm going to do exactly the same thing. But I'm going to replace that 27.9 by 27.9 divided by square root of 35. And I feel really lazy today, so I'm just going to actually type that in here. Even though I told JP in office hours, never do this. Because you learn when you retype it every time. Isn't that right?
Mm-hmm. I didn't learn anything.
You didn't learn when I told you that? Okay. So if we throw in those square root of 35s, well, the probability that the average for a group of pilots is less than 171 is basically 100%, as near as Excel can tell. The probability that the average weight of 35 pilots is less than 120 is 14. So that probability in between is 85. If you're designing an ejection seat, which one is more important? Thinking about individual pilots or pilots on average? Yeah, I think I'm not going to be ejecting 35 pilots at the same time. So,
Unless you have bell
well,
on
surely you're not going to have 35 pilots in the pilot seat on one plane. That would be pretty cozy. Yeah. All right. Examine the normal multiply population from normal distribution. Yeah, basically this is, I don't want to talk about that right now. It's close to a straight line. So, I don't remember exactly how that works off the top of my head. But as far as the answer to the question, it's yeah, because it lies on a straight line. I'm trying to think about how do you make one off the top of your head. And basically you're graphing the data versus how many standard deviations away it is. Look at that. Okay. I'm gonna double check that I'm remembering right just before I steer you wrong. This is a good place to pause the video anyway.